Hi, this is Dr. Habib Ahmed. Today I will demonstrate the breakdown voltage of gallium nitride PIN diode, a key factor in high power electronics. Using MATLAB, we will model how doping, depletion width, and impact ionization affect the breakdown voltage. Whether you are into semiconductor design or just curious about gallium nitride technology, you are going to love this. Here is the MATLAB code for gallium nitride PIN diode simulation. First, let me give you a brief intro into the topic. Gallium nitride PIN diodes are widely used in high power applications due to their wide energy band gap, high electron mobility, and high breakdown performance. Understanding the breakdown characteristics is crucial for designing devices that can withstand high voltages without failing. Key parameters influencing the breakdown voltage include the depletion width, doping concentration, and on resistance. Now, there are a couple of figures omitted for in order to gauge the performance of gallium nitride PIN diodes or even PIN diodes in transistors. One of them is Baliga's figure of merit and the other one is Johnson's figure of merit. And here are the equations for both of them. Baliga's figure of merit and Johnson's figure of merit are commonly used metrics to assess the performance of semiconductor materials for power devices, particularly for applications in high power and high frequency applications. Baliga's figure of merit is widely used to evaluate the suitability of semiconductor materials for power electronic devices. It quantifies the trade-off between the breakdown voltage and on resistance. So, for example, lower on resistance is more desired, and higher breakdown voltage are desired for power efficiency and minimizing power losses. Since gallium nitride has a higher breakdown electric field of approximately 3.3 megavolts per centimeter, high electron mobility, and relatively low permittivity, its Baliga's figure of merit is significantly higher than that of silicon or other traditional semiconductors like silicon carbide. This makes gallium nitride a superior candidate for high voltage and high power applications. Now let's talk about Johnson's figure of merit. Johnson's figure of merit assesses the trade-off between the breakdown voltage and the frequency of operation. It considers both the electric field, or you can say the critical electric field, and the saturation velocity of the material, making it more relevant for high frequency power devices. Gallium nitride has a high breakdown electric field and a reasonably high saturation velocity of approximately 2 × 10⁷ centimeter per second, which gives it a high Johnson's figure of merit. This indicates that gallium nitride is capable of high-speed switching at high power levels, making gallium nitride ideal for high frequency and high power applications like radio frequency power amplifiers and high voltage power converters. Here are some examples of gallium nitride based applications ranging from commercial to avionics to defense, and all these are possible because of the wide energy band gap and the compact design of gallium nitride materials. In high power semiconductor devices like gallium nitride PIN diodes, the breakdown voltage is also influenced by impact ionization, where energetic carriers, for example electrons and holes, gain enough kinetic energy from the electric field to ionize atoms, generate additional carriers, and initiating an avalanche breakdown. A common method for estimating the breakdown voltage performance involves using a power law expression based on material's critical electric field and doping concentrations. And this power law expression basically determines the breakdown dependence of gallium nitride PIN diodes on the I layer thickness and on the doping concentration. And the derivation of these equations are really extensive, but I have just listed down the most important equations over here, where alpha effective is the effective ionization coefficient for electrons and holes. E over here is the critical electric field. B and N are the fitting parameters, and this reference worked on the calculation, experimental calculation of these parameters, which came out to be to have these values, as you can see over here. For this is the value for B, and this is the value for N. Then here is the expression for the calculation of the depletion width. The depletion width in a PIN diode is the region where mobile charge carriers, electrons and holes, are depleted due to the built-in electric field. Then we have got an expression for the critical electric field as well, and here is another expression for the breakdown voltage. Breakdown voltage is the reverse bias voltage at which a significant increase in the reverse current occurs, causing the diode to enter avalanche breakdown. This depends on the material properties of gallium nitride as well as on the doping concentration and depletion width of the PIN diodes. So doping concentration actually plays a crucial role in order to find out both the depletion width and the breakdown voltage. Lower doping results in a wider depletion width and higher breakdown voltages due to reduced electric field intensity per unit length. However, the Bali gas figure merit, as we discussed in one of the previous slides, also depends on the on resistance of the devices. And here, and then further, the on resistance is a combination of the resistance of the drift region, resistance of the N and P type regions, and also resistance of the contacts. However, the resistance of the drift region dominates, so we can effectively say that the on resistance is approximately the resistance of the drift region, and it's equal to this expression. So a lower doping concentration increases the depletion width and it increases the breakdown voltage, but it also increases the on resistance, which negatively impacts the device performance in the forward direction. So here are the PIN diode trade-offs. In power semiconductor devices, there is always a trade-off between the highest reverse breakdown voltage and the low specific on resistance or the forward voltage drop. And then based on the interplay of these parameters, which is the doping concentration versus the breakdown voltage and the depletion width versus the breakdown voltage, and then its impact on the impact of the doping concentration on the on resistance, I performed some MATLAB simulations and then plotted the results. Like I plotted the depletion width versus the doping concentration, and then the breakdown voltage versus the doping concentration. Similarly, in another plot, I've demonstrated both the breakdown voltage and the on resistance versus the doping concentration. And then we can have codes where we can represent each of these independent variables versus doping concentration independently as well. Like for example, breakdown voltage versus doping concentration, depletion width versus doping concentration, and then breakdown voltage versus the I layer thickness. Similarly, the on resistance versus the breakdown voltage. And similarly, we can plot the critical electric field versus the doping concentration and the critical electric field versus the depletion width as well. Now let's talk about the MATLAB code. Excuse me. So here is the code that models the key characteristics of the gallium nitride high power pin diodes, such as the depletion width, the breakdown voltage, and on resistance across different doping concentrations, providing insights into the device performance. Let's break down the MATLAB code in the context of modeling gallium nitride high power pin diodes. I am going to explain each part in relation to the physical principles involved, particularly for gallium nitride material properties and high power pin diodes. So here are some basic parameters for gallium nitride. For example, ECC over here represents the critical electric field of gallium nitride in volts per centimeter. It's 310 to the power of 6 volt per centimeter. Gallium nitride is a very high breakdown electric field, making it ideal for high power applications. Then N over here in this MATLAB code is a material specific constant used in the modeling of breakdown voltage or depletion characteristics in gallium nitride. And this parameter is related to the empirical fitting or analytical model used for gallium nitride pin diodes. As I discussed in one of the slides, that I took this value from one of the references which found the fitting parameters N and B. So similarly, this value over here, B, is also a constant related to gallium nitride avalanche breakdown characteristics. It's an empirical constant that defines how breakdown voltage relates to doping concentration and depletion width. This E over here corresponds to epsilon or permittivity of gallium nitride. It represents the dielectric constant of gallium nitride, where 8.9 is the relative dielectric constant of gallium nitride, and 8.854 10 to the power minus 14 is the permittivity of the free space. Similarly, the small q, it is the elementary charge in coulombs, which is the charge of an electron. This line over here corresponds to the range of doping concentration in per centimeter cube, typically used for doped N region, like the doped I layer region, in this case for the gallium nitride pin diode. And gallium nitride devices often operate in this range for power applications. The 110 to the power of 19 is a little bit, not a little bit, it's quite on the higher side, but I wanted to demonstrate a range of doping concentration for the I layer. Then this equation over here is used for the calculation of the depletion width, and in micrometers for different doping concentrations, using a power law model often employed in high critical field semiconductors like gallium nitride. And I've copied this formula, I've implemented this formula from the slides that I actually showed over here. So here you can see the formula for W. Similarly, we can also calculate the critical electric field. This line over here calculates the critical electric field in the high power pin diode, which is the electric field strength where the breakdown occurs. And once again, I've implemented this equation over here in MATLAB. Similarly, I have calculated the breakdown voltage using this equation given over here for gallium nitride pin diode. Breakdown voltage represents the reverse voltage at which the diode enters into avalanche breakdown. So as you can see, here is the equation given over here, and I implemented the same equation in MATLAB. Then further, here I defined another range of depletion width. So the code so far is enough to demonstrate figures, these two figures. However, for these individual, for plotting each of these individual parameters, I have included more lines over here, like this W1. This creates a range of depletion widths starting at 0.01 microns and going up to 15 micrometers in this code, and this is further used for the calculation of the reverse breakdown voltage and the critical electric field and the on resistance as well. And for the on resistance, I'm using this equation over here. So I implemented the same equation over here in order to determine the on resistance for the high power gallium nitride PIN diodes. Then using this equation, I'm calculating the Baliga's figure of merit, which is a key parameter for evaluating the performance of power devices. It is defined as the square of the breakdown voltage divided by the on resistance, indicating a trade-off between the breakdown voltage and the conduction losses. And then after that, using the print command, this line over here, it prints the calculated values of the on resistance to the MATLAB command window, formatted to 2 decimal places. Then I have some subsections for in order to plot the results. The first subplot gives me depletion width, and so this one actually gives me the depletion width versus the doping concentration. Similarly, another subplot gives me the so these these lines over here from here to here plot depletion width and breakdown voltage versus doping concentration in the same plot. This line over here actually plots depletion width versus doping concentration on the left y vertical axis, and this one over here plots the breakdown voltage versus doping concentration on the right y axis, on the vertical axis. So it's actually a dual y axis plot. Similarly, over here I'm plotting the breakdown voltage and the on resistance versus the doping concentration in the same plot. The breakdown voltage is plotted on the left y axis, and the on resistance is plotted using the right vertical axis. And here I define the units, the font weight, the font size, etc., the labels, X label and Y label, etc. So let me move to slightly to the right so that you can see the rest of the code over here as well if you want to type it. Okay, so now I'm going to run the program now. Let me full screen it. Okay, and then we can go to edit and then figure properties. I'm gonna close it over here. click on this figure. I want to take it slightly further to the right, and I want to increase the width of it. Similarly, you can increase the size of this figure as well, and then you can play around like this vertical axis over here represents the breakdown voltage for the left figure. Similarly, this one is the breakdown voltage for the right figure. So you can play around with the values of each of the axis in order for a fair comparison. And similarly, you can play around with the colors of these as well. Let me move to and also I got another code where you can individually plot each of these parameters. So I'm gonna run this program now. And you can see depletion width plotted versus doping concentration, breakdown voltage plotted versus doping concentration. Similarly, breakdown voltage plotted versus I layer thickness, and breakdown voltage plotted versus and on resistance plotted versus the breakdown voltage. You can see some results over here as well, and you can see like I plotted 6 different figures, individual parameters over here as well. So you can have a combination of subplots depending on what you want in terms of the results that you want to plot or present. This was the modeling part, and the focus of this video is on the modeling part, but quickly I also want to show you that I performed an experimental study as well using metal modulated epitaxy, in which I grew gallium nitride high power PIN diodes. And you know that experimentally we run into non-idealities, defects, etc. We don't achieve the ideal results as given by the mathematics or the physics. So I fabricated gallium nitride high power pin diodes with I layer thicknesses of 1 micrometer, 2 micrometers, 5 micrometers, and 10 micrometers. And these are pretty thick devices, so I had to introduce a new fabrication method, and we are in the process of patenting that method as well. And then here is a complicated structure of those gallium nitride pin diodes, and I measured the doping concentration of the I layer, and it came out to be approximately 8 into 10 to the power of 16 per centimeter cube from capacitance voltage measurements. So for this doping concentration, the depletion width comes out to be approximately 2.4 micrometers, and the corresponding breakdown voltage comes out to be 450 volts. So this is the theoretical limit. For these devices, I was able to achieve a maximum breakdown voltage of 375 volts, which is not that far away from the theoretically achievable 450 volts. And these were actually the best quasi-vertical MBE grown gallium nitride high power PIN devices ever. So that's it. We have built a MATLAB model to calculate the gallium nitride pin diode breakdown voltage. We explored how doping and electric fields come into play. If you enjoyed this, hit like and subscribe for more tech tutorials. If you got any questions or ideas for future videos, drop them in the comments. Thanks for watching, and I will catch you in the next video. Take care. Adios.